All right, let's jump right in. Today, we're taking a look under the hood of what many are calling the world computer, Ethereum. Now, this thing is a revolutionary platform, no doubt about it. But trying to upgrade it while it's live, with billions of dollars on the line, that is one of the single biggest challenges in tech today. So, let's get into it.
You know, Ethereum holds this incredible promise to be the next evolution of the internet, powering a whole world of decentralized apps, or DApps. But there's a huge problem. If you've ever used it, you've probably felt it, right? It feels like you're stuck in a massive, planet-wide traffic jam. It can be painfully slow, and the tolls, what they call gas fees, can be just ridiculously high. So what's going on?
And this is why. Unlike, say, Google or Amazon, who can just spin up more servers when things get busy, Ethereum is totally decentralized. Every single computer in the network, every node, has to process and agree on every single transaction. Now, this is what makes it so incredibly secure and trustworthy, but it's also the very thing that causes that global slowdown. So how in the world do you fix a traffic jam when the road is the entire planet?
Well, that brings us to the first part of our story. We're going to look at a solution that cryptographers have come up with that is honestly kind of like magic. It's a way to get out of that traffic jam without giving up any of that core security.
The big idea is something called a ZK rollup. So just imagine this. What if you could take, say, 1,000 transactions, bundle them all together, and do all the heavy lifting on a quiet side street, completely off that clogged up Ethereum main highway? Then you just post one tiny, super secure receipt back to the main chain that proves, without a doubt, that all that work was done correctly. This would just slash the traffic on the main road. And the tech that makes that magic receipt possible is called a zero-knowledge proof, or ZKP. Now, the key phrase here, the really mind-blowing part, is zero knowledge. It means you can prove that something is true. Like, yep, I processed those 1,000 transactions and followed all the rules, without revealing any of the actual details of those transactions. It's like proving you have enough money in your account to buy something, without ever showing anyone your bank balance.
A really famous way to wrap your head around this is the Alibaba cave analogy. Picture a cave that's shaped like a ring, with a magic door blocking the path on the inside. Now, to prove you know the secret password to that door, you walk into the cave alone. Your friend, who's waiting outside, then randomly yells either "come out path A" or "come out path B." If you know the password, you can always open that magic door and come out the right way. Do this enough times, and your friend is 100% convinced you know the secret, and you never, ever had to tell them what it was. That's the power of a ZKP.
But, and this is a huge but, what if there's a typo in the magic spell? The code that creates these proofs in systems like Halo 2 is just unbelievably complex. And if there's one tiny bug in there, something called an under-constrained circuit, the result could be catastrophic. It could literally let someone create a proof that looks totally valid for a completely fraudulent transaction. It would be like letting them print money out of thin air. We've seen similar issues with protocols like Tornado Cash, so this is a very real danger.
So obviously, we need a way to check this code for bugs before it's unleashed on the world. And that's the first huge breakthrough from the research we're talking about today. The researchers built the first ever tool that can automatically scan these Halo 2 circuits. Basically, it translates all that crazy crypto math into a simple, logical language that a powerful bug hunting engine, called an SMT solver, can check. Think of it like a super-powered spell checker for logic, hunting down those dangerous flaws before they can do any harm.
So here's what that looks like, basically. The analyzer takes the circuit code that a developer writes, translates it into a language the SMT solver can understand, and then the solver just checks it for errors. It's like having a universal translator that lets you find bugs in some of the most complex code ever created. This is a massive step forward for making Ethereum scaling solutions safe. Okay, so we've found a way to tackle the traffic jam, but scaling is only half the battle, right? That's just one piece of the puzzle. We still have to secure the actual applications running on this new, faster network. So let's move on to part 2, building a smarter digital bouncer. I mean, think about any app you use. It has rules about who can do what. Some people are admins, some are just regular users. That's called access control. And in the world of decentralized finance, getting access control wrong isn't just a minor bug. It can lead to people losing hundreds of millions of dollars.
And this isn't some theoretical what-if scenario. This happened. Just look at the Poly network hack. A simple mistake in how the system determined who was allowed to do what led to one of the biggest heists in crypto history. Over $600 million vanished. The stakes for getting this right are just unbelievably high.
Now, traditionally, developers have had two main ways to handle this. On the one hand, you've got role-based access control, or RBAC. It's simple. You're an admin or a user, and you get the permissions for that role. But it's super rigid. If you need a bunch of different custom permissions, you end up with a role explosion, just tons of roles to manage. On the other hand, there's attribute-based access control, or ABAC. This is way more flexible. It can check specific things, like is the user over 18, or is this transaction happening during business hours? But man, it can get really complex really fast.
You can really see the difference here. On the left, RBAC is nice and neat, users are put into buckets, and each bucket gets certain permissions. Simple. On the right, ABAC is way more dynamic, checking all these different conditions before it lets you in. They both have their pros and cons, but neither one is really perfect for the kinds of complex apps being built today.
So what do we do? Well, this research proposes something brand new, a hybrid model they're calling role-centric access control. And the best part is, it's designed as a kind of plug-and-play service for developers. The goal is to get the best of both worlds, simplicity and power.
So here's the brilliant part. It starts with the simple foundation of RBAC. You give a user a main role, but then you add a flexible layer of ABAC on top of it. This lets you add really specific, fine-grained rules. So for example, you could have a trader role, but then add an attribute-based rule that says, okay, but traders from this specific company are not allowed to borrow these specific assets. It's this flexible, layered approach that gives developers a ton of power without making things a nightmare to manage. Okay, but here's a super important question. Is this thing actually practical? Because on Ethereum, every little computation costs money. It costs gas. So the researchers tested it. And what this chart shows is that as you add more of those attribute-based rules, the ABACs, the cost of a transaction goes up in a really predictable straight line. No crazy spikes.
And it's the exact same story when you add more roles. The costs scale in a very predictable way. Now, why does this matter so much? It proves that this awesome new security model isn't just some cool idea on a whiteboard. It's an efficient, affordable tool that developers can actually use in the real world to make their apps way, way safer.
All right, let's pull all this together. What do we learn? First, Ethereum's biggest problem is scaling without sacrificing security. ZK proofs are the answer for speed, but they're so complex they create new security risks. That's where the new automated bug finding tool comes in. It's a huge deal. Then, on the application side, we learn that flexible access control is absolutely vital, and this new role-centric model gives developers a powerful, practical solution to that problem.
Okay, wow, that was a lot of pretty deep, cutting-edge tech. Think you got the main ideas? Let's do a super quick pop quiz just to make sure it all sticks. First up, what is the main benefit of using zero-knowledge proofs for Ethereum scalability? The answer is B. It's all about moving the heavy lifting off the main chain to reduce that network traffic jam.
Question number 2, what's the main security risk in that complex Halo 2 code that the new analysis tool helps prevent? The correct answer is C. Those sneaky, under-constrained bugs are the ones that could let an attacker basically create money out of nowhere. And for our last question, the role-centric access control model is a hybrid of which two classic models? And the answer is A. It combines the simplicity of role-based access control with the power and flexibility of attribute-based access control. So what's the big takeaway here? It's that the actual building blocks for a faster, safer, better decentralized internet are being put into place right now. This kind of research is solving the really tough, fundamental problems of both speed and security. The tools are becoming available. The only question left is, what amazing things are we going to build with them first? Thanks for joining me.